Hi, the sorting algorithms that we have seen so far actually function by comparing the elements in the arrays. These algorithms are known as comparison sorting algorithms. In today's lecture, we will be using the decision tree model to show that any comparison sorting algorithm that we have seen so far must be lower bounded by n log n in the number of comparisons it makes over n elements in the worst case. We will then be looking at three sorting algorithms that run in linear time. These algorithms are the counting sort, radix sort, and bucket sort. Obviously, the big omega n log n lower bound does not apply to these three algorithms. So far, we have seen that the big O n log n bound is satisfied by merge sort and heap sort in the worst case. Quicksort achieves this bound on average. So we can always have a permutation of the input sequence that would impose a running time complexity of big omega n log n. We also learned how to develop the randomized quicksort using random sampling in the selection of the pivot element for the partition procedure. All the sorting algorithms seen so far are called comparison sorts, and they work on the basic idea of pairwise comparison of the elements. In other words, comparison sort uses the three basic comparison operations to order the elements in an input sequence denoted here by A1, A2 up till AN. So for any two elements AI and AJ, either AI is less than AJ, AI is equal to AJ, or AI is greater than AJ. If all the elements are assumed to be distinct and not repeated in the input sequence, then the equality test would make no sense and therefore it would be useless. Also, AI less than AJ is the same as saying AI greater than AJ, and they only differ in their output. That is, if we assume that AJ is greater than AI, then AI less than AJ would return true, and AI greater than AJ would return false. So we can reduce the three comparison tests to simply AI less than equal to AJ. The comparison sorts are best represented using decision trees, which are basically full binary trees where each node denotes a pairwise comparison test. We know that for an input with n elements, there are n factorial number of possible permutations. So this tells us that there should be n factorial number of leaves in the decision tree. The leftmost path is driven by the less than or equal to comparison operator, and any branch to the right is the greater than comparison operator. In this example, we have A1 is equal to 6, A2 is equal to 8, and A3 is equal to 5. The root 1 column 2 basically means that perform the test A1 less than equal to A2. So 1 and 2 are the indexes of the elements. If true, then branch to the left, else branch to the right. Comparing all the three elements leads us to the highlighted path, which is this path, which sorts the elements as A3, A1, and then A2. The first linear time sorting algorithm that we will learn today is called the counting sort. There is one assumption that makes this algorithm run in linear time, and that is each input element should be an integer in the range 0 to k, where k is an integer. So if the value of k is bounded by n, that is k is equal to big O of n, then the counting sort runs in theta n time. Now, why is it called counting sort at all? This is because it places each element x from the input in its current position by determining the number of elements that are lesser than x and placing them before it. Keep in mind that the elements are not compared using the comparison tests that we have seen so far. We will shortly see how it works. So if there are 17 elements with values lower than x, then the counting sort will put x in the 18th position in the output. There, however, is a small glitch, and that is for multiple elements with the same key value, the algorithm will place all these elements in the same position. So let's see how we can take care of this. Given array A from 1 to n as the input, we make use of two arrays, namely B1 to n and C0 to k. Since we use additional arrays, it goes without saying that the counting sort is an out-of-place algorithm. In the pseudocode, we first create the array C of size k plus 1 because it starts from 0, and then initialize all the elements of the array with 0 in the for loop shown over here. In the second for loop, we see that Ci now contains the number of elements equal to I. And in the third for loop, Ci would contain the number of elements that are less than or equal to I. Note that in these two loops, we do not use any comparison tests. Finally, from line 10 onwards, what we do is we place the elements in the right position in the output array B. Now let's visualize how the counting sort works using this example where k is equal to 5, n is equal to 8, and the array A is of length 8, and we have an auxiliary array C of length 6. We see that the array C has all 0 elements, which is the initialization step, which is done by the for loop on line 2. The for loop on line 4 counts the number of times each value is repeated and places it in its position in the C array. For example, it first looks at 2 and it goes to the second house and it increases this by 1. Then it looks at the value 5, it goes to the sixth house and it increases it by 1. It does the same for 3, 0, 2, 3, 0, and 3. So basically line 4 would change the C array as such. Now, after applying the for loop on line 7, we get the cumulative array shown in B. It means that the values in each house I tells us how many elements of the input array have values less than or equal to I. So house 0 tells us there are 2 elements that are less than or equal to 0 in the actual input. So we see that actually we have 2 zeros. So house 1 tells us that there are 2 elements which have values less than or equal to 1, which basically is the same 0. And so house 2 tells us that there are 4 elements that have values less than equal to 2. And if we count, we see that we have 2 2's and 2 zeros. So what we do in this stage is that we add up the values in each two consecutive elements and we move along the C array. So 2 plus 0 would be 2, and then 2 plus 2 would be 4, 4 plus 3 would be 7, 7 plus 0 would be 7, and 7 plus 1 would be 8. And that is basically what we have over here. Lastly, the loop on line 10 takes aj, where j iterates from n down to 1, and puts it in b of c of aj. It means that it uses the value of aj as an index in array C, which in turn is the index in array B. So starting from the last element, which is 3, we go to C3, which over here is 7. And then over here, we use this as an index. That means we go to B7 and we put the value 3 in the position 7 of the B output array. And we keep doing this until we reach this stage. So basically, if you look over here, by reducing or by using C as a counter, we actually can keep track of elements with the same values. To see that the counting sort runs in linear time, Let's look at the four for loops in the pseudocode. The for loop on line 2 iterates k plus 1 times, so it is theta of k. The second for loop on line 4 goes from 1 to n, therefore it is theta n. The third for loop on line 7 goes from 1 to k, so its running time is the same as the first for loop, that is theta k. The last for loop on line 10 iterates n times, giving us theta n. Since k is assumed to have a value of at most n, On will be the dominating running time as compared to OK. Therefore, the running time would be theta n. So it beats all the algorithms that we have seen so far, and it is not a comparison sorting algorithm. Another important property of the counting sort is that it is stable. That means if we have repeating values in an input array, then the position in which they appear in the output array would be would be maintained as compared to the position of the other elements with the same value. So if we look back at the example, since we had two twos, so the position of the twos in the initial input array will be maintained. That means the first two will never occur or will never happen to be placed after the second two anytime throughout the sorting process. Radix sort, another interesting sorting technique and one of my favorites, was used to sort the punch cards in the older days. I'm pretty sure that most of you may have not seen a punch card, forget about using it. The reason for being so confident is because I have never seen or used one. This is how a punch card looks like. It has a number of rows and number of columns where certain positions were marked as black or punched out to represent certain characters. Back then, being a programmer was not as easy as today. They had to punch a bunch of such cards to implement a simple program as an assignment submission. So be thankful. To sort the cards, an operator had to arrange the cards in different packs or bins. That means all cards that were punched in the first column were put in one bin, the cards punched in the second column in another bin, and so forth. So now let's use an example to illustrate how radix sort works. Suppose we are given a list of 3-digit numbers and asked to sort it. Looking at the input list, we can imagine the numbers as digits in 3 columns. Take the leftmost column and sort it. Pay attention that if 2 or more elements in the column share the same value, sort them as they appear in the input. Do not switch their positions. In other words, the digit 7 corresponding to number 457 appears before the digit 7 of number 657 in the actual input. This order should be maintained even after sorting them in the leftmost column. So we see that 457 appears before 657. After sorting the leftmost column, sort the numbers using the middle column. Finally, sort the numbers using the rightmost column. What we have in the end is a final sorted list. This sorting is mainly useful when we want to sort records that are keyed using multiple fields. Take, for instance, the telephone book or diary where dates are sorted using the year, month, and day. The code for the radix sort is very straightforward. In this procedure, let us assume that we have an array of n elements and each element has d number of digits, where digit 1 is the lowest order and digit d is the highest order digit. So in the pseudocode, we see that we have inputs a and d. We have a for loop which goes from 1 to d, and inside the for loop, we use a stable sort algorithm like the counting sort to sort the array A on each of the digit I. There is an lemma which states that if we are given n numbers, each of d digits, then each digit can take up to k possible values, and The radix sort would correctly sort these numbers in theta d times n plus k amount of time, if the sorting algorithm which we use in the for loop is a stable sorting algorithm. The proof is out of the scope of this course. As another example, let's use radix sort to sort a list of 3-character words from the English vocabulary. So if we are given these words and we start sorting from the leftmost column, this is what you would get. Now my question is, what happens if you start sorting from the rightmost column instead? Would you still get it sorted in the ascending order, or would it be sorted differently? The answer is that it would be sorted based on the last character in each word. The last sorting algorithm for today is the bucket sort. The average case running time of this algorithm is big O of n. Similar to the counting sort, where we made an assumption of the values that k can take, the bucket sort also runs fast, assuming that the elements are uniformly distributed over an interval 0 to 1 and generated independent of each other. In this technique, the interval is divided into n number of equal size subintervals called buckets, in which the n inputs are placed into. The final sorted output is then obtained by simply sorting the elements in each bucket and then traversing through each bucket in order. So, with the assumption that each of the n inputs is normalized to some value between 0 and 1, the pseudocode of bucket sort would look something like this, where we use an extra array B of n linked lists to represent the buckets. In the example over here, array A contains 10 elements with values from 12 to 94. To make it fit in the 0-1 interval, we normalize the array by dividing the elements by 100. Doing so results in the input array shown over here, where every element now is between 0 and 1. On line 3, the for loop basically initializes the array B to be empty. The loop on line 5 takes every element in array A and places it in the bucket using the expression B of floor n times AI. In our example, since n is equal to 10, it takes AI, let's say 0.78, multiplies it with 10, which gives us 7.8, takes the floor, which is 7, and then uses this as the index of the bucket into which 0.78 should be put. That means B of 7, which is over here, and we put 0.78 as shown here. After placing the elements into their respective bins, the for loop on line 7 sorts each bin using insertion sort. After insertion sort, we concatenate the list from B0 to Bn-1 and we give that as the output. Now you may wonder why we use insertion sort. The reason is because the list is broken down into smaller lists and placed into buckets, and therefore sorting each bucket would have lesser number of elements in them, and therefore insertion sort wouldn't perform bad. Also keep in mind that the bucket I in the array B will hold the values from the input that lie in the interval I divided by 10 to I plus 1 divided by 10. Now let's do the running time analysis for bucket sort. Consider two elements, say AI and AJ, such that AI is less than or equal to AJ. Since this expression holds, element AI would either go into the same bucket as AJ or into a bucket with a lower index as compared to the bucket of AJ. Now, if both of them are in the same bucket, then according to the for loop on line 7, they will be put in the right order. But if they are in different buckets, then line 9, which is a concatenation operation, puts them in the proper order. So we observe that all the lines except for line 8 would take O(n) amount of time in the worst case. Line 8 is the insertion sort. Now we need to analyze the total time taken by the n calls to the insertion sort on line 8. We use the random variable ni to denote the number of elements put in bucket bi. We also know that the insertion sort has a quadratic running time. Therefore, the recurrence equation for the running time of the bucket sort would be T of n is equal to theta n, which is contributed by the for loop on line 5 and the n number of calls to the insertion sort. As usual, we now take the expectation on both sides of the recurrence equation and apply linearity property to arrive at this. So if we can prove that the expected value of ni square would reduce to something that is linear, then we would basically prove our running time. So this proof is actually given on pages 202 to 203 of your textbook, where we see that E of ni square basically is equal to 2 minus 1 divided by n, which is linear. And therefore, we can conclude that the theta n plus n times O of 2 minus 1 divided by n would basically be theta of n as n grows asymptotically large.